Hello, my name is William McKinney, and I am a sophomore mechanical engineering student here at Cal Poly Pomona. Under the guidance of Dr. Farbad Kushnaud from the Electromechanical Engineering and Technology Department, I am working on a research project titled Performance and Dynamic Stability of a Variable Pitch Drone Under Turbulence. Our study aims to bridge the gap of knowledge in addressing turbulence in the commercial drone and UAV space. Work has already been done on using fixed-pitch propellers to address this turbulence. We have reason to believe from previous experiments that variable-pitch propellers will offer performance advantages over fixed-pitch propellers in these turbulent environments. We hypothesize that variable-pitch propeller mechanisms will allow a drone to perform better under turbulence by responding to commands from the onboard computer faster, holding its target position more closely, and taking less time to reach its target position. This will be a starting point for future research involving this subject. It is well known in the aviation community that variable pitch mechanisms allow pilots to maintain an airplane's maximum efficiency and exert an extra degree of control over their aircraft. Variable pitch propellers are not a new idea. The earliest variable pitch quadcopter was created in 1922. The first patent for an automatic variable pitch mechanism was awarded in 1929. Variable pitch mechanisms were implemented in World War II-era airplanes, and other attempts at experimental aircraft used variable pitch mechanisms as a method of control soon after. More recently, researchers at MIT's Aerospace Controls Lab quantified and verified what pilots already knew instinctively. Variable pitch mechanisms provide more control over an aircraft by providing a greater change in thrust than only changing the speed of fixed pitch propellers. They can even reverse the thrust output, effectively allowing aircraft to decelerate faster than gravity to stop overshooting their target position. Furthermore, research conducted at Lodz University of Technology in Poland showed that the maximum achievable thrust of a propeller could be increased by 31%, and its efficiency as much as 7.5%. In terms of generating turbulence, some testing sites have been created to generate ranges of turbulence intensities, like UC Merced's Data Drone Test Site and Stanford's Multipurpose Wind Tunnel. These kinds of environments have put fixed-pitch propeller drones to the test, but not variable-pitch drones. This is where we hope to fill in missing knowledge and data. Several practical builds can be found on YouTube to create one-axis drones for testing system control loops. Several key theories can be extrapolated from the current body of research. Variable pitch mechanisms can increase the performance of drones for acrobatic or demanding flight regimes, and turbulence can be created in a wind tunnel environment. We believe that high levels of turbulence creates greater acceleration demands than traditional quadrotors can supply. For example, drones crash out in the field after being flown on windy days. Therefore, we hypothesize that the variable pitch mechanisms will combat turbulence better than fixed-pitch propellers. Our experiment will consist of measuring the thrust output of the motors we are using, while varying their speed to determine equations we can use in our control software. We expect both the speed and pitch to linearly increase the thrust output, and that there will be a point at which increasing the pitch will cause the propellers to stall. The motors, mechanisms, microcontroller, and other parts will be combined into a drone that will rotate on one axis. The motors will be first flown without actuating the variable pitch mechanism, which will give us an understanding of the performance of the fixed pitch concept. The next round of experiments will be done while actuating the pitch mechanisms. The experiments will be conducted in an open circuit wind tunnel consisting of wooden panels and a box fan. So far, I have been able to construct the wind tunnel according to the required specifications and collect wind data with a wind speed sensor. I programmed an Arduino Uno to take the voltage output of the wind speed sensor and convert those signals to a wind speed in meters per second, all the while recording those values onto an SD card for processing. The wind tunnel allows us to test at 3 different fan speeds. Wind speed measurements were taken at several positions throughout the airflow at different heights, depths, and distances from the edges of the tunnel. 5 depths and 4 positions at every depth were tested. 4 different heights were tested in each position and depth as well. All of these positions amounted to 2,400 measurements, 10 measurements for each position, depth, and height taken every second for a total of 10 seconds per measurement. This has resulted in some initial findings. As shown in these graphs, the wind speed is asymmetric and variable at different heights and positions across a constant depth. This indicates turbulence across the cross-section of the wind tunnel. However, surprisingly, there was a consistent increase in speed as depth and fan speed increased for the same distance from the edge of the wind tunnel. This indicates that there is not turbulence in the depth dimension of the wind tunnel. Theoretically, we predicted that the fan would produce a maximum Reynolds number of over 120,000. Generally, Reynolds numbers are indicative of levels of turbulence. Any number over 4,000 is turbulent. Experimentally, the maximum Reynolds number was 101,000, which is about 84% of the expected value. The maximum turbulence intensity of a point in the wind tunnel, another indicator of turbulence levels, was 6.535%, which is consistent with and within the bounds of what has been experimented with before. While this is not as turbulent as has been achieved in similar experiments, it is acceptable for a homemade wind tunnel. The project is constrained to the limitations of the budget. Ideally, this experiment would be conducted in a professional environment with more controlled turbulence values. Here are examples of how the drone will be impacted by the wind pattern in the wind tunnel perpendicular and parallel to the wind direction. Perpendicular to the wind direction, the drone has a tendency to rotate with the airflow, and while facing the wind, it reaches a stable equilibrium. Initial progress has been made in controlling the motors with an Arduino Uno microcontroller. The microcontroller in this video uses the input of a potentiometer to turn on and change the speed of the motor. This is all powered by a battery, which is then being relayed to an electronic speed controller. The electronic speed controller uses a battery eliminator circuit to power the Arduino. The signal is then sent through the Arduino and the electronic speed controller to the motor. In the future, the motor will be able to be controlled only by computer commands from the Arduino. From the initial results, we can conclude that the wind tunnel produces significant turbulence that can be used in an introductory experiment. We also proved that an Arduino and motor can be run off the power provided by the battery eliminator circuit in an RC-grade electronic speed controller. Further work needs to be done with more professional equipment to verify the results of this experiment.